In this next lecture, we're going to continue our discussion of the transport layer. This time we're going to be focusing on TCP. So specifically, we're going to talk about segment structure, reliable data structure, and flow control. We're going to skip connection management and principles of connection management. We already covered that in 475, so you should have a good handle on that. We're going to focus on TCP, the specifics of TCP congestion control. Basically, TCP is defined in multiple RFCs. We have them here. Hopefully, I'll have the time to put some links in the additional materials section so you can look them over. But basically, we're going to discuss the general overview of how TCP works. So basically, a TCP basically sets up a point-to-point connection between a sender and a receiver. This is different from, say, like a UDP broadcast. This is basically a single point-to-point connection. And basically, we set up a reliable in-order byte stream. So as we've mentioned previously, you use TCP when you have to have a reliable connection where we have to set up. You can't have things out of order, and you don't care about time, because it obviously takes more time to set up a connection, but you do care about data reliability. We have the ability to do pipelining, like we talked about. We talked about the different pipelining. Let's just go back in, and we can do that in TCP. We'll talk about how that works. Basically, also TCP is full duplex, so you can have a bidirectional data flow in the same connection. So one side can be sending data and the other side acknowledging, and vice versa within the same connection. And there's a maximum segment size that we're going to talk about, which is basically the maximum transmission unit minus the header. So we're going to talk about that a little bit more later on in the lecture. And basically, this is one of the overheads of TCP. Overhead of TCP is that it's connection oriented. Okay, this is what gives you your reliability. But as to the overhead of TCP, there's some basic handshaking, some exchange of control messages that initiates the sender and the receiver in a specific state before data can be exchanged. So we basically make sure that we have a connection set up, and then we exchange data. And there are flow control mechanisms within TCP, which we'll talk about, so that the sender does not overwhelm the receiver. Basically, remember, we want this to be reliable, so we can't be reliable if the receiver can't receive all the data, so we have to throttle back sometimes. So we have some flow control mechanisms. This is what the basic TCP segment structure looks like. So starting from the top, obviously we have our source port number and our destination port number. We talked about that TCP uses a 4-tuple for connections with the sender and receiver IP address, which is in the layer below, and the source and port number, which is in the TCP segment. We have our sequence number, an acknowledgement number. This kind of when we go back and forth, we're going to see an example of this. And these basically count. These numbers are a count of the bytes of data that's being sent. And this is used to determine to determine whether or not your data has been lost or not. We'll see that when we go back and forth. We'll see the example of a sender and a receiver and how they use a sequence number and acknowledgement number. We have this flag that says an acknowledgement number is valid. We have PSH, which is definitely not used anymore. We have urge for urgent data, also not used. We have R, S, and F, RST, SYN, and FIN. These are used for connection establishment, setup, and teardown commands. We're going to see examples of this in some later slides. There's a checksum, just like in UDP. There is the receive window, which is going to be the number of bytes the receiver is willing to accept. This is used for flow control. And then you have some options, which we'll talk about later, and then the actual data. So when we do the Wireshark lab, you'll get to see this being populated, and will kind of help bring home what this segment actually looks like when a TCP connection is in use. Okay, let's talk a little bit about how the sequence numbers and acknowledgements work. So here we have an example, graphical example here. So imagine you have this is on the sender side. You have these packets in green where an acknowledgement has been sent. You have your sliding window, which starts at the first packet that's been sent and not acknowledged, so all these are in flight. You have these blue ones that are usable because they're within the window, and these are gray that are not usable. So let's say at this point in time I'm just about to send this blue one, and basically this blue packet here, this first blue packet, has a sequence number, and that is the number of the first byte in the segment's data. So if you count the bytes in each one going forward within for a particular message, for a particular byte stream, it's whatever that number of that byte is. On the acknowledgement side, in the acknowledgement we send the sequence number of the next byte expected from the other side. So basically, when the sender gets the acknowledgement back, this basically acts like a cumulative acknowledgement, because this tells me if the sequence number expected is what I would expect the receiver to look for. So the question is, how does the receiver handle out of order segments? And basically it varies depending on different implementations of TCP. So we're not going to get into the details of how that happens, because that's going to vary. So just to kind of bring the point home, let's talk a little bit more about sequence numbers. Hopefully this will start making some sense. So like I said in the previous slide, the sequence number for a segment is the byte stream number of the first byte in the segment. So imagine, for example, you have host A wants to send a stream of data to host B via TCP. The data stream consists of a maximum segment size, which is the MTU. We talked about this previously. The MTU minus the header of 1,000 bytes, and the first byte is numbered 0 because that is the first byte in the segment. So to send a particular message, it's going to construct 500 segments out of the data stream. So we have 500 segments. Each of them are going to have what? they're going to have 1,000 bytes in each segment. So the sequence number in the first segment is 0 because that is the number of the first byte in the segment. So it's going to be 0 through 999. So the second sequence number is going to be 1,000 because that's the number of the first byte in that particular segment is byte 1,000, and the third is 2,000, etc., etc., until we sent all 500 of our segments. So hopefully this really helps you understand what we're talking about as far as the sequence numbers go. So what about the acknowledgments? So suppose host A has received all bytes numbered 0 through 535 from host B, and suppose it's about to send a segment to host B. Therefore, host A puts 536 in the acknowledgement field, the acknowledgement number field of the segment that is sent to host B, because host A has received 535 bytes from host A has received 535 bytes from host B. So when remember this is bidirectional, so when host A sends data to host B, it puts 536 in the acknowledgement field so you're basically acknowledging what was sent previously, and I'm sending new data at the same time, and I'm putting 536 because that's telling host B, hey, I received up to 535 bytes. I'm expecting byte 5. I'm expecting that you're sending me byte 536 next. Now, if host B already sent byte 536 and it gets that in the acknowledgement field, it knows that something's wrong. If it really did just send 0 through 535, it gets 536, then it knows everything's okay. So here's another example. So suppose you have two hosts, host A and host B. Okay, host A initiates a telnet session with host B. Each character typed by the client is sent to the server and echoed back to ensure the character is seen by the telnet user is processed at the remote site. Host A has a starting sequence number of 42, and host B has a starting sequence number of 79. So, in this example, the client types a C and he walks away from the screen. Client types a C. It sends a message with a sequence number of 42, an acknowledgement number of 79, because that's host B's starting sequence. So that's the last time it was received, and the data, which is the letter C. The host acknowledges the receipt of C and echoes back C. So we're sending the data payload back, and we're also acknowledging the previous message. So it sends a sequence number of 79, which was the next one it was going to send. It acknowledges 43 because it's saying, okay, you sent me sequence 42. I expect 43 is going to be the next thing you're going to send me. And indeed, the host acknowledges the receipt of the echoed C. It's not doing anything else. Whoops. Not doing anything else because the user left the screen. So it sends a sequence number 43 and an acknowledgement of 80, which is the next sequence number for host B. Okay, so next we're going to talk a little bit about reliable data transfer and how that works with TCP. In TCP's reliable data transfer, TCP creates a reliable data transfer service on top of IP's unreliable service. It basically uses the concept of pipelining. It uses the concept of cumulative acknowledgements, and it uses a single retransmission timer. These are all concepts we just talked about in the previous lecture section. Now we retransmit if a timeout occurs. We wait too long to get a timeout, or if we receive duplicate acknowledgements. So let's take a look at an example of how the TCP sender works. We'll look at a simplified example. We're going to ignore for the moment duplicate acknowledgements. We're going to ignore flow control and congestion control. So in our TCP sender, when the data is received from the application above us, we create a segment number with a segment with a sequence number. And the sequence number, like we just said, is the byte stream number of the first data in the segment, of the first data byte in the segment. We start our timer if it's not already running. And basically the timer is for the oldest unacknowledged segment. So this is kind of like go back N. And we have an expiration interval called the timeout interval, where if that is reached, then we're going to resend the unacknowledged packets. We're going to timeout. We're going to retransmit the segment that caused the timeout and restart the timer. If an ACK acknowledges a previously unacknowledged segment, we're going to update what is known to be acknowledged and restart the timer if there are still unacknowledged segments. So let's take a look at a state diagram of this simplified TCP sender. We start off in our initial setup with next sequence number is set to initial sequence number, and send base is also set to initial sequence number. We receive data from the application. We create a segment and a segment number equal to next sequence number. We pass the segment to the IP layer. Then we update the next value of next sequence number based on the length of the data. And if the timer is not currently running, we start the timer. Now thinking about a sliding window for a second, an acknowledgement received with the acknowledgement field value of Y. If Y is greater than send base, we set send base equal to Y. And if there are currently not any unacknowledged, not yet acknowledged segments, we start the timer. If there are currently not acknowledged segments, we start the timer. If that's not the case, then we're going to stop the timer. And that's basically a state diagram that illustrates what we just talked about. So let's take a look at that, looking at a timeline. So here we have our timeline. We have host A, and we have host B. Host A sends a packet with a sequence number of 92 and has 8 bytes of data. The acknowledgement that's going to come back is going to be the next number expected, which is 92 plus 8, which would be 100. That gets lost. So basically, there's no acknowledgement. The timeout value eventually is exceeded. So then host A will resend, and then host B acknowledges, and then we can continue. We don't set a timeout because we got our acknowledgement back and got it in time. Here's an example where we have a premature timeout. So the timeout value has to be a reasonable value based on the round trip time. Sometimes we don't have a good timeout value, and we can time out prematurely. This is an example. So we start out with host A. Again, in this example, send base is equal to 92. We put 8 bytes of data in the segment, and we're doing some pipelining. So we send another packet of data. Now we have a sequence number of 100 because 92 plus 8 was 100. And that's going to have 20 bytes of data. Host B receives both. It acknowledges the first one with an ACK of 100. It acknowledges the second one with an ACK of 120, adding 20 bytes to what's expected. But what happens is, unfortunately, it took too long, or this value wasn't set correctly. I resend this value, and I resend back 120. So now I'm doing a cumulative acknowledgement. So now we know that both of these messages were sent to the receiver, and now I can start off. I can update a send base to 120, and I can use that as my starting point for my next message that I send out. Here I have have host A. It's doing pipelining, so it sends a message. The first one with sequence number 92, the second one with a sequence number of 100. Host B acknowledges both. This acknowledgement gets lost, but this acknowledgement gets sent because the timeout value was long enough. Losing this acknowledgement wasn't a really big deal. Once I get this cumulative acknowledgement, I know that I'm good. I know that host B received both packets. So now I can continue. I can update send base and send my next packet with sequence number of 120.